Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. In part A, that was actually divided into two video segments, we discussed some basics of supply chain and supply chain management and some related terminology, and three decision phases in a supply chain. In this first segment of part B, we will see two perspectives that we can take with respect to supply chain management. So there are two ways to view the processes performed in a supply chain. That is, we know that supply chain is the sequence of processes and flows that take place within and between different stages and combine to fill a customer need for a product. So this flow of material and information and cash can be seen in two different ways. We will focus more on flow of information and material. So one is cycle view. The cycle view is the one that we have seen so far in different figures and flow diagrams. And we will see it again in a more detailed way. The processes in a supply chain are divided into a series of cycles, each performed at the interface. We saw there are different interfaces in any supply chain between two successive stages of a supply chain. So at every interface between two parties in a supply chain, there is a cycle that is repeated. So we will see how that happens. The second is push-pull view. The processes in a supply chain are divided into two categories depending upon whether they are executed in response to a customer order or in anticipation of customer orders. The pull processes are initiated by a customer order, whereas push processes are initiated and performed in anticipation of customer orders. So let's first see the cycle view of supply chain, and you can find this figure from the book by Sunil Chopra. So this is what we have seen so far, that there is a manufacturer or the channel master or nucleus firm, and on the left side are different suppliers. In this case, you have three suppliers, and there are the distributors, there are retailers, and there are customers. Now there is an interface between two parties. For example, there is an interface between supplier and manufacturer. There is another interface between manufacturer and distributor, between distributor and retailer and customer. So there is a cycle that actually repeats at each interface. What that cycle is, so we have drawn the same figure, conceptually the same figure. In reverse order. So at the top is the customer, and then there is retailer, and so on. So what happens is that actually customer places order with the retailer. So that is the flow of information. Then retailer, for example, delivers the product to the customer, and then customer pays the retailer. Of course, sequence can be slightly different, but this is a cycle that repeats at the interface between customer and retailer. There is another interface, for example, between retailer and distributor. So for example, retailer places order with distributor, that is the flow of information. Distributor delivers the product to retailer, that is the flow of, that is the physical flow, the flow of product, for example. And then retailer pays the distributor. So that is again essentially the same cycle that is repeating. And again, another cycle could be between distributor and manufacturer. So distributor places order with the manufacturer, that is flow of information. Manufacturer delivers the product to distributor, so that is the physical flow, and distributor pays the manufacturer, so that is the flow of cash or flow of money. And of course, another cycle, conceptually the same cycle, is at the interface between manufacturer and supplier. Manufacturer places order, flow of information. Supplier delivers the components or the material, that is the flow of materials, that is the physical flow, and then manufacturer pays the supplier, so that is the flow of the money or cash. So essentially the cycle is the same, that is repeating that is being repeated at each interface. Now, of course, these all things are interrelated, they are integrated. So actually the cycle is one, and these cycles are sort of sub-cycles of a bigger cycle. So actually, ultimately, The demand that is being satisfied is the demand of the customer. But in order to fulfill that demand, there is a demand generated by retailer that is satisfied by distributor, and demand generated by distributor and satisfied by the manufacturer, and manufacturer's demand is satisfied by supplier. But ultimate source of demand is customer. So you can say that there is a bigger cycle of information flow, and that actually starts with the customer and ends with the supplier. And there are different cycles for the flow of components, materials, and product, but that actually starts with the supplier and that ends with the customer. So that was the first cycle, a flow of information. Its basic source was customer and it ended with the supplier. And then product flowed, in fact, components or raw materials flowed from the supplier and ended up with the customer. And of course, the third flow of the cash, so its main source was customer, and it ultimately, of course, after satisfying the demands of retailer, distributor, and manufacturer, also being the supplier. And in order to fulfill this the requirements of this bigger cycle, there are small cycles at different interfaces. Now, practically, there is a problem, and that problem relates to this first cycle, because this cycle is the central, that is the flow of information, because other two flows depend upon this. Now, based on the flow of information, the products are made, and of course, based on the products that are made and sold, the cash flow takes place. So this flow of information, that generally the customer is the source of that information. This information gets distorted because of different reasons. And one reason is what we call JIC. That is not a standard abbreviation, but just like we call just in time. So there is a thinking that is called just in case. So for example, retailer asks customer for its demand and customer says, okay, I need 100 items. So customer places an order of 100 items. So retailer, for example, places an order of 110 with the distributor, just in case there is another customer or there is more demand. And for example, this distributor places an order of say 130 with the manufacturer, just in case the retailer asks for more or there is some surge in demand. And for example, manufacturer places an order of say 170 with the supplier, just in case there is more demand, and supplier makes, let's suppose, 200 components or 200 assemblies that are required to make the product. So that is a very serious problem that happens in daily life as well. So that is called bullwhip effect. That is called bullwhip effect. So we'll see it in detail in the module on forecasting. So that was a cycle view of the supply chain. So there are three V's of actually supply chain, and one of them is visibility. Visibility. So one way is to avoid actually bullwhip effect is to increase the visibility of information within the supply chain. And we will see later how we can actually do that. And there are, of course, other reasons of bullwhip effect as well. Not only the distortion of information, but some other factors that we will see in the module on forecasting. The second view is push-pull view. Now we are aware of what push process is and what pull process is. Pull process is executed in response to customer order. So we know the demand, and once we get the demand, we actually start the process. So that is a pull process. So this is a reactive process. Reactive means we don't do anything, we don't make anything unless we receive the exact order. The second type of processes are push processes. They are initiated in anticipation, not in response, but in anticipation. We do something beforehand. So demand is not known exactly, and it must be forecasted. So pull processes are reactive, push processes are speculative because they respond to speculative demand. So they operate in uncertain environment because customer demand is not yet known. But both pull and push processes in a supply chain are interrelated. Both are used together in order to meet the demand. As we saw in different figure that there are processes that are being performed in sequence in a flow. Now, this is a very important decision in many cases to decide up to which point we will have push processes and from where will the pull processes start. And that sometimes becomes a strategic decision. So in this figure, you can see that organization, or you can say the supply chain, has a series of operations to be performed. Series of operations are to be performed. So process 1, 2, 3 up to process n. So some processes are performed in this case as series of push processes, and then there are a series of pull processes. And this point sometimes becomes very important to be decided. Sometimes the organization can decide the limit to which push processes will be performed, and from there onward pull processes will start. So that point is called push-pull boundary or decoupling point. Now this decoupling point is very important, decoupling point. So that is very important to be decided in some cases. And that can actually benefit the organization significantly. So I give you a couple of examples. One example is example of a football league, or you can take an example of basketball league. So that runs for many months, for example. So I have this full case study, and I will inshallah provide you as well. But the basic idea is that the organization that made shirts, replica shirts, that spectators or the fans wear during the season of that league. So it had to forecast the demand for the shirts. So based on forecast, it made the shirts, printed them, and for example, then sold them. But what actually happened was that some favorite teams or some best teams, they started to lose the matches unexpectedly, and some teams that were not highly ranked, they started to win and progress in the league. So the teams, of course, they were losing, their shirts sold less in number, and the teams that were winning, their shirts sold in greater number. So the result was that some shirts, replica shirts, were out of stock, and some shirts were actually not sold. So what the organization did was that it delayed the printing process. So it made, for example, just to get an idea, the white shirts, printed some of the shirts based on some figures, some numbers, but kept the rest of the shirts, and from time to time, from say week to week, it saw the demand of the shirts that was increasing, and then printed the, for example, player number, player name, or whatever color of the shirt that they required according to the demand. So that resulted in more fulfilled demand, more sale of the products, and less stockouts and less extra inventory of the shirts that were not sold. So in this case, the organization actually shifted the decoupling point toward the customer. They delayed, for example, the printing process unless they had the demand known for certainty. They knew the exact demand. The printing process was delayed. Another example that can be taken is, you know it very well, that is a very simple example, that is some fast foods, for example. So you know that in many fast foods, some processes are push processes. For example, they may make the recipe or dough or something like that beforehand, and then may, for example, mix those ingredients according to the demand or according to the customer requirement. So one possibility is that everything is done when the customer order is received. That is some organization do. In this case, push-pull boundary will be too much on the left side. If everything is ready-made, for example, burgers, so of course they are not fresh, or the push-pull boundary is near to the customer, but of course customers actually requirements are not there incorporated in that product. So one option is to do few things beforehand, push processes, and try to take this push pull boundary as near to the customer as possible, but keep some activities that depend upon customer orders for which the product sells. That is the critical point. You have to postpone, or you have to delay the activities that are value adding and that are the source of customer satisfaction. So that is also a critical decision, that which activities we are going to delay. So in this case, printing was that activity. So in the case of fast food, you can think of some activity that actually satisfies the customer most. So you could delay it. For example, filling the toppings or whatever is the factor that satisfies the customer most. So you could delay that. The third example is example of HP printers. So there are different voltage standards in different countries. So initially the HP made printers, and the printer cable was the standard part of the printer. So for example, the cable or whatever is the specification of the cable, they were for, let's suppose, 110 volts, so they won't work with 220 volts. So they made the cable separately and they delayed the assembly process. That is simply inserting the cable into the printer. That will be the step when the printer is to be used. So they made the cable separate and they made the printer separate. And depending upon the customer order, they packed the cable that was suitable for that voltage. So in this case, they of course change the design in each case. This is very important, that this is not that simple. You need to redesign the process if you are shifting the push-pull boundary to either side, to upstream or downstream. So you have to redesign the process. So in that case, of course, HP had to redesign the product as well as process so that cable could be inserted separately. So it was packed with the printer whenever the customer order came. So relevant cable was packed with the printer. So another example is paint manufacturing. So I think this is the example of ICI. So instead of making the final paint, they made the base paint and they added the pigment when the order for certain color of the paint was received. So the main takeaway is that you can move the push-pull boundary toward the customer. The more you can, the better it is in general, but it is important to be decided which activity or which process actually should be delayed. That should be the process that is more valuable, that is the cause of customer satisfaction. And shifting the push-pull boundary may require the redesigning the product or redesigning the process. So that is not that simple. So this decision should be taken with caution. So what you are doing is you are postponing some activity, some process. So that is why it is also called postponement. And what is to be postponed or delayed? Something that differentiates the product. So it is also called delayed differentiation. So postponement or differentiation, delayed differentiation can have different forms. Here you were delaying a process, that was the printing process. Here you were sort of delaying the packaging process, which cable should be packed with which printer. In the case of painting, you were delaying or postponing assembly process, joining two things. In the case of fast food, maybe again here was an assembly or joining process, but it could be labeling process. For example, you make the cartons for your products, but every country requires certain labels on the packaging cartons. So according to the country, you could label the cartons differently. So you could postpone or delay different activities, not only manufacturing activities, but it could be other activities as well. So based on this decoupling point, this is a strategic decision. I have given you different examples. So we can classify manufacturing systems according to the decoupling point. So we can see what are the four types of manufacturing systems based on the location of decoupling point. So we have four types: engineer to order, make to order, assemble to order, and make to stock. In engineer to order, the decoupling point is at the extreme left. So you can say there is as such no decoupling point because all activities here are pull activities or pull processes. So there is no push processes. Uh, there is no push process involved. So as said, there is no decoupling point. So in engineer to order, the word engineer here is a verb. So that is designed to order. So customer just tells you the requirements and you have to design the products according to the requirements. You have to purchase the components and materials for that product, manufacture the product, assemble it, and ship it. In make to order, this is the decoupling point. So you have the inventory of generally raw material available, then customer order comes here. So you make the product according to the order, assemble it, and then ship it. In assemble to order, this is the decoupling point. So you have inventory of generally components or sub-assemblies here. Generally, these are the sub-assemblies. And when the customer order comes, you assemble the product and ship it to the customer. And finally, in the make to stock, decoupling point is further near to the customer. You have manufactured a product, assembled the product, and you have inventory of the finished product here. And here does the customer order come and you deliver the product. So here, this was the push process and these series of pull processes. In the case of make to order, here push activities and then pull activities. Here all these are push and the pull activity to ship the product to the customer. Just notice that this word inventory has different meanings here. You might have observed. So this is the inventory of generally raw material, maybe components as well. Here it is the inventory of semi-finished products or sub-assemblies, maybe some finished components as well. So raw material, components and sub-assemblies, and here it is the inventory of finished goods, right? So raw materials, sub-assemblies and finished goods. Now some examples of each. So in example of engineer to order, a technical example is Descon engineering. So that Descon actually designs the chemical plants according to customer requirements, then purchases the components and material for those plants, constructs those plants, assembles those plants, and then installs those plants. So that is an example of engineer to order organization. So all products that are designed and manufactured according to customer requirements are example of engineer to order. Example of make to order is, for example, furniture. So the furniture maker has the inventory of, let's suppose, raw material, that is the wood and nails and whatever is required to make the furniture, glue, etc. And then you tell the requirements, and according to those requirements, using the same common material, common starting material, different types of furniture is made. So that is a common feature of make to order, that the raw material or the starting material is the same, and using the same material, different products within the same family of products are made according to customer requirements. Or your clothing can be an example, suits. So you have the fabric, standard fabric available, but You tell your specific requirements, your specific, for example, size and other design that you require. And then the suit or the shirt or whatever is stitched according to your requirements. So that is example of make to order. Assemble to order, the classical example is personal computers, most easy example to understand. So what happens is that, for example, you go to a Hafiz center, so there is an inventory of um, RAMs and hard disk and motherboards available. You tell your specification that you need personal computer with this much RAM, this much hard disk, and this much, uh, for example, specification of motherboard, etc. And then that computer is assembled according to your requirements. So that is assembled to order. And make to stock is most easy to understand. So all your consumer items are example of make to stock. So soaps, shampoos, tissue papers, the other packaged material, consumer items, sugar, salt, etc. All these are examples of made to stock. So you might have noticed that delivery lead time is different in different cases. So delivery lead time is the highest in the case of engineer to order because it includes the time for design, purchasing, manufacturing, assembly, shipment, etc. It's slightly less in the case of make to order because it starts with manufacturing, assembling, and shipment. Assemble to order is further less, and then make to stock because it has only delivery lead time for shipment. So customer just goes to the general store or retail store or, for example, some mega store and just places the order, gets the product, pays the money, and that is the story. One very important point you should be attentive to is that this assemble to order can be used for achieving high variety. So you can say that assemble to order is a specific example of delayed differentiation. Using the same components, I can have a different personal computer assembled, the same stock of component that a retailer has, and you can have a totally different personal computer from the same stock of components of a computer. So we can have in this assembled to order, that is a specific case of delayed differentiation. We can have uh, low. Let me write here. In the case of assembled to order, we can have low physical inventory and high effective inventory. Now, what does that mean? What does that mean? So, for example, let's take the same example that I have three things on which personal computer depends. So, for example, that is RAM, hard drive, and let's suppose motherboard. So, I have, for example, four types of RAMs available. And let's suppose I have three types of hard disks available. And for example, two types, or let's say three types of motherboards available. My question is, how many computers can I make? So let me tell you the quantity as well. So let me, for the sake of simplicity, tell you that I have, for example, 5 RAMs of each type. So I have 20, 5 hard disks of each type, 15, and 5 motherboards of each type, so 15. So I have 20 RAMs. In simple words, I have 15 hard disks and 15 motherboards. And out of 20, 5 are RAM type 1, 5 are RAM type 2, 5 are RAM type 3 and RAM type 4. Similarly, out of 15 hard drives, 5 are type 1, 5 are type 2, and 5 are type 3, and similarly for motherboard. So my question is, how many types of computers, how many combinations, let me call it, how many combinations of computers can I make? How many combinations? What are the possibilities? For example, like I give you further explanation. For example, one possibility is that I use RAM type 1, hard drive type 1, and motherboard type 1. So this is one computer that I can have. Another possibility is that RAM type 1, hard drive type 1, but motherboard type 2. Third possibility is same RAM and hard drive, but third motherboard. And then you can have RAM type 2, hard disk type 1, motherboard type 1, and you can continue with it. So how many types or varieties of computer can I have? And second question is, how many computer actually can I make? Of course, assuming other things to be constant with these quantities. Maximum कितने computers मैं बना सकता हूँ? Think over it and you will get the answer that the less physical inventory, that is the inventory of actual computers I will eventually make, and high effective inventory, that is the options that I have to make different types of computers. Push type supply chains are forecast driven and pull types are demand driven. So we'll come to this point in some topic later. So here are examples. We have seen most of them already. So example of make to stock, departmental store, ready to wear suits. आप जाते हैं, you go to the market, tell your collar size, purchase the shirt. So that is a simple example, or in simple words, all consumer items are example of make to stock. Like painkiller here, for example, Panadol or other medicine that you just pay the money and get from the pharmacy are examples of make to stock. So these are most common types of products that we use in everyday life. Example of assemble to order. We saw this example just in the previous slide. So consumer or retailer laptop computers, you go to the market and get the combination that you require. So that is an example. Another example is a razor manufacturer that has, for example, razors available, and on the other side, different sizes of, you can say, the packaging material are there. So, for example, smaller packaging material, relatively larger, and for example, third size. So in this, for example, packaging material, you can say like 5 razor, here you can 10, here you can 15. So according to your requirement, the shopkeeper just packs the number of razors. So that is also an example of assembled order. So here you need packaging material of different sizes and razors. Make to order. So fabric, just I gave you an example, is an example of make to order. If you have standard fabric available and you get your shirt or your clothing stitched according to your requirements using standard fabric, so that is make to order. Furniture is another example, and you, for example, make some other products according to your own requirement, like maybe housing is another example as well. So your standard bricks and mortar available, cement available, but if you ask someone to make some construction for your requirements, if design is not involved, that is example of make to order. So example of engineer to order. Example of engineer to order, as we saw, DESCOM, software development in the case of service organization. So design and manufacturing both are involved. So that is the basic difference between make to order and engineer to order as well. So for example, cruise ship, you ask for the cruise ship to be designed and then to be made. So that is an example of engineer to orders. Technical example another could be molds and dies as we saw in the previous course. So if you are asking someone, you are telling the requirements that I have to make this product and design the die or mold for it and also manufacture it. So that is also example of engineer to order. So the basic difference between engineer to order and assemble to order is that components are yet not specified unless design is finalized. But in make to order, the common components or raw material is used, but the product is made according to your requirements. So you can think of more examples as well. So if we draw volume on the x-axis and variety on the y-axis, so engineer to order processes are mostly project based. So you can think of almost all project based organization to be engineer to order. Make to order and assemble to order mostly use intermittent processes like a batch or sometimes maybe job shops. And as you move to make to stock, so they are flow processes. So they might be using assembly lines or mass processes. If you move to the nature of tasks, so in projects, tasks are diverse and complex. Skill level required is very high. And each project is different than the previous one. And as you move down to make to stock, the tasks are repeated, divided. So here the concept of specialization is involved. There is more automation involved. So here we focus on economies of scale. And as we saw in the previous slide, that lead time is very high in engineer to order, and that reduces as you move down from make to order, assemble to order, and that is shortest in make to stock. So I will recommend you to further ponder over these two slides. This is very important. We will need it over and over again in this course. Think of some more examples of each type of process and try to analyze this graph further. So these are the two views of the supply chain, cyclic view and push-pull view, and we will, for the most part in this course, focus on push-pull view. But very important is that once we move from one module to the next, we will again discuss the interface that we are at, as we saw in the first type of view, that was the cycle view. So you should keep both in mind, and we will refer to them in this course over and over again. Thank you very much.